to the Mathematician's podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we're indulging ourselves with the life and mind of one of the most influential thinkers of the ancient world, Eudoxus of Cnidus. Now, I used to have a friend who was a baker. One day, a customer asked him to bake an enormous pie, about 31.4 centimetres in radius. I mean, it would have to be big enough to fit all those blackbirds. But my baker friend was up to the task, and with a puff, the pie was ready. When the customer asked for it to be delivered, the baker cheerfully replied, "Shoo, whatever you like." But when he arrived at the customer's house, there was only a small letterbox through which to post it. And this is where he got philosophical. Armed with a rolling pin and a playful attitude, he began dividing the pie into ever smaller slices, gently posting piece after piece through the tiny slot. As the blackbirds chirped in confusion from inside the crust, the pie, like a problem too big to solve all at once, was delivered bit by bit. My friend's method might not win awards, but it's a great reminder that even the most daunting tasks can be tackled if you just break them down. Sometimes, to solve a problem, you just have to start. Let me give you another example, one that you can play with yourself. The challenge is to start with my baker friend's large pie and split it into pieces, but specifically, we're going to explore the number of ways to divide the pie into a set number of pieces. The rules are we will only count a new pie dissection, or pie section if you prefer, as distinct if it uses a different cutting strategy, i.e. you must drag the knife in a different pattern as opposed to just different sized slices. You could think of this almost like topology, where the shape doesn't matter, but the arrangement of the shape is important. Moreover, for this study we do not care about the equality of the servings, but a more interesting analysis would be to also constrain equal areas. My other rule is that each cut must bisect something. In other words, I can't use 4 slices to cut out a perfect square from the middle, even though this is usually how I would serve myself. So, to summarise these rules, every cut must cut the pie into at least 2 sections. We're looking for new ways to cut the pie into a set number of total sections. So let's get cutting. How many ways are there to cut the pie into one serving? 1. We don't cut at all. We have one pie. I eat it for myself. I am a happy boy. Okay, how many ways are there to cut the pie into 2 servings? Again, only one way. The one way we can do it is one cut, and all of these cuts must be identical because they just go from circumference to circumference, and therefore there is only one method of dissection to cut the pie into 2 pieces. Okay, how many ways are there to cut the pie into 3 servings? 2 different ways. We could cut 2 lines where each has both endpoints on the crust, or cut one line crust to crust and the other crust to middle. How many ways are there to cut the pie into 4 servings? Well, I can count 9 distinct options that obey the rules above, but it's not obvious that this is an exhaustive list. And sadly, I cannot find an authoritative source online, so I guess I am becoming the authoritative source online and saying there are 9. Go and draw them for yourself. One of my colleagues at university had a similar problem for his master's thesis, except it was cutting a sphere into equal areas. He didn't find an answer either. As far as I can tell, this problem fits into that delightful nook of mathematics that is easy to do on the back of an envelope. I would happily challenge my students to cut a pie into slices in 9 different ways. It is conceptually easy to do. However, the solution is unknown, in that there is not yet a formula that will predict how many ways you can cut a pie into, say, 10 slices. The only method available to us to solve these sorts of problems is just to have a go. Carefully define the problem and then exhaust all the possibilities. Today's mathematicians wield powerful software and supercomputers to solve equations that would make your head spin. But in Eudoxus's time, they had none of that. What they did have was ingenuity, persistence, and a deep understanding of geometric principles. And believe it or not, these ancient mathematicians solved problems that set up modern calculus and astronomy, all with nothing more simple than tools and their own intellectual grit. Eudoxus is a perfect example of this mindset. His work shows us that with enough patience and precision, even the most complex questions can be tackled, one small step at a time. So, grab a cup of coffee, settle in, and let's journey back to the 4th century BCE. To understand Eudoxus, we first need to place him in context. Eudoxus was born around 408 BCE in Cnidus, a Greek city in Asia Minor, modern-day Turkey. Cnidus was known for its intellectual and cultural vibrancy. It boasted impressive temples, a thriving economy, and, perhaps most fittingly, a passion for learning. From an early age, Eudoxus displayed a natural curiosity. While we don't have personal diaries or letters, ancient Greeks weren't that big into biographies, anecdotes tell us that Eudoxus's thirst for knowledge drove him to travel far and wide. One story claims that as a young man, Eudoxus journeyed to Athens to study under none other than Plato. Eudoxus isn't mentioned in the dialogues, which is a notable absence. This could be because their views conflicted so much that Plato did not want to honour him with the fame. It is possible that Plato gave him the pseudonym Philebus, as these nicknames have similar meanings. But Athens wasn't his only stop. Eudoxus's wanderlust took him all the way to Egypt, where he studied with the priests of Heliopolis, shaven head and eyebrows all round. Here he studied Egyptian astronomy and geometry, disciplines deeply entwined with their religious and agricultural practices. The Nile, after all, demanded precise measurements to manage its flooding. It is said that Eudoxus was so dedicated to learning that he endured a great deal of hardship. According to one tale, he travelled to Egypt with barely enough money to sustain himself. Despite his financial struggles, he impressed the Egyptian priests so much with his intellect that they granted him access to their closely guarded astronomical knowledge. This dedication, this relentless pursuit for understanding, is a hallmark of Eudoxus' legacy. Now, let's talk about mathematics. One of Eudoxus' most significant contributions is his method of exhaustion. And no, it's not about tiring yourself out with calculations, though I've certainly been there. The method of exhaustion is an early precursor to integral calculus, developed over 2,000 years before Newton and Leibniz came on the scene. Interestingly, the method of exhaustion wasn't invented by Eudoxus. It was first introduced by Antiphon, who used it as a way to approximate the area of a circle. Unfortunately, Antiphon didn't develop the method fully or rigorously enough to gain widespread recognition. While Antiphon didn't get his own episode here on the podcast, his idea paved the way for Eudoxus, who expanded and significantly refined the technique. I should clear up a small and intentional misconception here. In my introductory ramble, I gave you 2 examples, but only one of them relates to the method of exhaustion. When we use it in the ancient Greek sense, we mean finding an area by dividing a shape into progressively smaller sections, until the total area has been exhausted. The other more interactive puzzle of cutting a pie into n pieces would be better described as a proof by exhaustion, which has a much wider definition. Eudoxus applied the method of exhaustion to solve problems like approximating the value of pi by inscribing polygons within a circle and increasing the number of sides. This geometric approach allowed him to exhaust the difference between the polygon and the circle, achieving remarkable precision. This might sound familiar to you because the method is often associated with Archimedes, who will absolutely get his own episode. Archimedes took the method to new heights, famously using a 96-sided polygon to achieve an even better approximation of pi, But it's essential to remember that while Archimedes stretched the method to its limits, he didn't invent it. That credit goes to Eudoxus, who drew the first triangle for these later advancements. Let's bring this into a modern classroom. Suppose you're teaching students how to approximate the area of a parabola. You could draw the curve on the graph and inscribe rectangles underneath it, calculating the area of each rectangle. As you increase the number of rectangles and make their widths smaller, the total area of the rectangles gets closer and closer to the true area under the parabola. This process mirrors the method of exhaustion, using smaller and smaller steps to approximate an area with greater precision. But amazingly enough, it is also the first intuitive look at integral calculus, a link that spans 2,000 years of mathematical development. Another example might involve finding the volume of a cone. Imagine slicing the cone horizontally into thin discs. The method of exhaustion allows us to approximate the cone's volume by adding up the volumes of these discs. The thinner the slice is, the more accurate the approximation becomes. A challenge for you then. Could you use this approach to find the surface area of a sphere? What shapes would you need to use? Perhaps we could focus on the hemisphere first. If we draw a set of lines from the centre to the rim, then we will split the hemisphere into triangles. Each triangle will have a height that is a quarter of the circumference, pi r over 2. This is because it goes from the pole to the equator. And the circumference will be shared equally between the number of triangles n. Therefore, each triangle will have a base of 2 pi r over n. Again, this is because the equator is equal to the circumference and we have n triangles. So the area of each triangle is half the base times the height, which is a half times pi r over 2 times 2 pi r over n, which gives you pi squared r squared over 2n. We can then multiply this by the number of triangles to get the area of the hemisphere, and double it to turn that hemisphere back into a full sphere, and that yields a total surface area of pi squared r squared. Oh, hang on, that's not right. It should be 4 pi r squared. I wonder if you could do any better. Now, let's take a moment to appreciate the sheer brilliance of this method. It's not my whimsical misapplication, which I do use as an example for my students of when not to trust a proof that sounds convincing. But in a time when numbers were represented with Greek letters and abacuses, Eudoxus was pushing the boundaries of mathematical abstraction. His work demonstrates not just the technical skill, but also a deep understanding of the principles underlying geometry. Some people may argue, however, that what Eudoxus proposed is not really rigorous. Maybe we could take a moment to explore how he actually proposed the method and how it relates to the modern standard. Long quotation coming up. If from any magnitude there be subtracted a part not less than its half, and if from the remainder once again subtracts not less than its half, and if this process of subtraction is continued, ultimately there will remain a magnitude less than any preassigned magnitude of the same kind. Or in the modern epsilon notation, if there is a magnitude m and any small magnitude epsilon, and if there exists a ratio r such that a half is less than or equal to r which is less than 1, then there must exist a p such that m times 1 take r to the power of n is less than epsilon for all values of n greater than p. If it walks like real analysis and quacks like real analysis, then it's probably real analysis. 2,000 years before real analysis. Eudoxus's other monumental achievement lies in his theory of proportions, which addressed one of the most perplexing challenges of ancient mathematics, the existence of irrational numbers. Let's rewind for a moment. Greek mathematicians loved whole numbers and fractions. They were comfortable with ratios like 3 to 2 or 7 to 5, but then Pythagoras and his followers discovered something unsettling. The square root of 2 couldn't be expressed as a fraction. Or in other words, the length of a diagonal was not an integer ratio to the side length of the square. This realization threw Greek mathematics into a philosophical crisis. How could something as fundamental as length defy the rules of rationality? Eudoxus came to the rescue. he developed a rigorous definition of proportionality that could handle both rational and irrational quantities. His theory stated that two ratios are equal if, for any multiples of the terms, the relationship between the first and second terms matches the relationship between the third and fourth. To put it simply, Eudoxus redefined proportionality in a way that bypassed the need to directly confront irrational numbers. By not requiring the ratio of two integers, this elegant solution restored mathematical harmony and became a core definition of Euclid's Elements. In fact, Book 5 of the Elements is essentially a tribute to Eudoxus's theory. It's worth noting how revolutionary this was. Eudoxus's theory didn't just solve a technical problem, it shifted the philosophical underpinnings of mathematics. He showed that abstract reasoning could overcome the limitations of numerical representation, a lesson that we still must teach, even today. As well as being an exemplary mathematician, Eudoxus was also a pioneering astronomer. He developed one of the earliest known models of the universe, a geometric system of homocentric spheres. Here's how it worked. Eudoxus imagined that the Earth was at the centre of the cosmos, and that the celestial bodies were embedded in a series of concentric spheres. Each sphere rotated at a different speed and along a different axis, producing the complex motions we observe in the sky. For example, he used 27 spheres to explain the movements of the Sun, Moon, and planets. While Eudoxus's model wasn't entirely accurate, it couldn't account for the phenomenon like the retrograde motion of the planets. It was a groundbreaking attempt to explain celestial mechanics using mathematics, and it inspired later thinkers, including Aristotle and Ptolemy, to refine their own cosmological theories. Beyond mathematics, Eudoxus was also deeply interested in questions of ethics. While he's primarily remembered for his scientific contributions, ancient accounts suggest that he explored the philosophical foundations of human happiness, as indeed we all do. Eudoxus proposed that the ultimate goal of life is eudaimonia, often translated as a flourishing or well-being. He believed that pleasure played a crucial role in achieving the state, but unlike the hedonists who pursued indulgence for his own sake, Eudoxus argued that pleasure was the natural end of human action, a guiding principle rather than a fleeting desire. This nuanced perspective suggests a connection to the ideas of hedonism, though Eudoxus framed his views with a broader ethical context. This nuanced perspective suggests a connection to the ideas of hedonism, though Eudoxus framed his views with a broader ethical context. Interestingly, his ethical philosophy influenced later thinkers, including the Epicureans, who also emphasized the importance of pleasure as a component of the good life. However, Eudoxus's emphasis on balance and intellectual pursuits set him apart from more indulgent interpretations of hedonism. For Eudoxus, true happiness came from aligning one's life with the harmony of nature and reason, a perspective that resonates with his mathematical and astronomical views. He may have annoyed Plato, but he had a glowing character reference from Aristotle. Aristotle writes in the Nicomachean Ethics that Eudoxus showed excellence of character and was considered remarkably temperate. Now, let's talk about how we know what we know about Eudoxus. Unfortunately, none of his original work survive. Like much of ancient Greek science and mathematics, Eudoxus's contributions come to us second-hand through later authors. The most significant source is Euclid, whose Elements incorporated Eudoxus's work on proportions. Archimedes also referenced Eudoxus's method of exhaustion, praising its rigour. Additionally, Aristotle provides valuable insights into Eudoxus's cosmological and ethical ideas, though not always in great detail. Later historians, such as Simplicus in the 6th century CE, preserved fragments of Eudoxus's astronomical theories. One topic we have not discussed with Eudoxus is that he reportedly is the first person to notice that a year is 365 and a quarter days long. These accounts, though indirect, paint a picture of a polymath whose influence permeated diverse fields. It's a testament to the intellectual ecosystem of ancient Greece that thinkers like Aristotle and Archimedes ensured Eudoxus's legacy endured. But this also leaves room for mystery. How much of Eudoxus's work was lost? What might we learn if we could unearth even a single manuscript? These unanswered questions remind us of the fragility of history and the importance of preserving knowledge for future generations. As we near the end of our journey, let's reflect on Eudoxus's legacy. His influence extended far beyond his own lifetime. His mathematical methods were instrumental to the work of Euclid, Archimedes, and later mathematicians in the Islamic Golden Age. But who was Eudoxus as a person? Accounts describe him as deeply curious, incredibly disciplined, and despite his achievements, humble. One story claims that Eudoxus preferred a simple lifestyle, living in a modest home and devoting his days to study and teaching. He was above all committed to the pursuit of knowledge for its own sake. It's humbling to think about the intellectual courage of figures like Eudoxus. In a world without modern technology, without calculators or telescopes, he dared to tackle the mysteries of the universe, armed only with his mind and a piece of papyrus. Thank you for joining me on this exploration of Eudoxus of Cnidus. I hope his story inspires you to approach mathematics not just as a set of rules and formulas, but as a way of thinking, a lens through which we can understand the beauty and complexity of our world. If you enjoyed this episode, don't forget to subscribe and share the Mathematician's podcast with your friends and colleagues. For all the remainder of this week, we will be counting down the days until our next great mathematician, Xenocrates. There are a myriad reasons why you should listen along. Until then, goodbye. The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.